Hello and welcome to the Big Technology Podcast, a show for cool-headed, nuanced conversations of the tech world and beyond. Let me tell you, I'm pinching myself that we're actually about to have this conversation because I think it's going to be the most fascinating we've had on the podcast, bar none. And let me tell you why. So in 2017, I got a chance to spend some time with Yann LeCun. And Yann was the head of Facebook AI research. Now you might know the company as Meta. He's the chief AI scientist there. And we spoke a lot about how you can actually take the human mind and make it artificial, turn it into something that's an AI. And I think that that's making a thinking machine is Yann's long-term goal. Then this summer, I had some time off and decided that I was going to read a book I wanted to get around to for a long time. And it was Thinking Fast and Slow by the Nobel Prize winning professor Daniel Kahneman. And as I'm reading this book, I start thinking, wow, like Professor Kahneman describes the way the mind works in so many interesting ways that I hadn't thought about, and ways that you'd imagine Yann would have to think about if he wants to build a thinking machine. And so why don't we just get the two of them together? Obviously, it was a pipe dream, right? Anyway, about a month ago, I'm in the same room as both of them by some stroke of luck. And I propose, why don't we have this conversation? So, of course, I go up to Professor Kahneman, we'll call him Danny for, this conversation, and say, hey, have you ever spoken with Yann? And it turns out that they've spoken many times, and this is discussions they've had in private a handful of times, but they've never had it in public. And so we'll have it in public today. So first of all, I want to say Yann and Danny, welcome to the show. It's great to have you both.
Pleasure to be here.
I think we should just do the foundational stuff about what Yann's mission is, a little bit on Danny's research, and then actually stay tuned for the second half because Danny brought a list of questions that he wants to ask Yann, and I'll just take a back seat for that. But why don't we start here? Yann, I'd love to hear a little bit more about if you could briefly share your ambition to build a thinking machine, and like what does that actually look like? Do you want to replicate the human mind one for one?
No, I don't want to replicate the human mind. I want to understand intelligence. I think one of the most fascinating questions of our time, scientific questions of our time, is what is intelligence? How does the brain work? The other two fascinating questions of our times are what is life all about, and how does the universe work? Right. So, these are like big questions, and as a scientist and an engineer, I consider that I don't really understand how something works unless I build it myself. So, or have some understanding of how to build it. And so the purpose of AI is there's a dual purpose. One is understand intelligence, perhaps approach models of human intelligence if we want. And the other one, of course, is to construct interesting artifacts that can help people in their daily lives and make the world better and everything.
Yeah.
So I think it's really two purposes: the scientific one and the technological one.
Right. And just to follow up on that, I mean, I remember sitting with you in your office you were talking about, how, you want to teach computers how to predict. And if they can predict, they can plan. And then if they plan, they can start to have some functionality that, we have as human beings. And there is this rush towards general intelligence where folks like you and researchers in your stratosphere are attempting to build a thinking machine. So that's right.
Well, yeah. So the first question is, or the first thing you can notice in the animal world is that there is no intelligence without learning, and
Mm-hmm.
in the engineering world, it's almost true as well. And it's probably because I'm either lazy or not smart enough that I think that as human engineers, we cannot actually directly conceive and construct an intelligent machine. We have to build a machine that can make itself intelligent through learning, right? So that's how I got interested in learning. That was very early on, like when I was an undergrad or something. And then the next question is how to get machines to learn. And of course, there's a long history of machine learning, supervised learning, starting with the perceptron and things like that. And what has become really clear over the last couple decades, it was clear. It was even clear for people like Jeff Hinton before that, but maybe just for me is that the type of learning that we are currently able to reproduce in machine, which is supervised learning and reinforcement learning, do not seem to reflect what we observe in humans and animals. There is another type of learning, another
Mm,
paradigm of learning that seems to take place in humans and animals that allows humans and animals to learn how the world works, mostly by observation, a little bit by interaction, but mostly by observation. And we accumulate enormous amounts of background knowledge about how the world works. And that connects with with things
yes.
that Danny talks about.
Hmm.
If we have a model of the world, this model of the world we can use it to plan because we can imagine the result of the consequences of actions we're taking. That allows us to plan. So this is what Danny calls system two. Okay, but currently what we can do with machine learning is more like the system one, the stuff that
Hmm.
here is an input, here is an output that does not require reasoning, if you want. So we're sort
Yep.
of, I'm interested in sort of trying to get machine to learn models of the world so that we can get them to reason, essentially.
Yeah, it's so amazing to have you both on the same show because now we get to go to Danny to talk a little bit about these concepts in terms of the way that the human mind thinks, and then we can go back to you, Jan, and think about how we might be able to get that into AI. So, Danny, at the risk of having you go through the Freebird speech of that you make often, but I think it's important for listeners, especially those who haven't read the book. Are you able to just describe a little bit more what Jan is talking about in terms of the way human beings think, and talk a little bit? I know it's sort of a shortcut, but talk a little bit about System One and System Two,
Yeah,
and give us
well,
an overview there.
I would say that when we describe human intelligence, we speak of a representation of the world, and it's the representation that leads to prediction. That is, there is no shortcut to the prediction from the data. You go through a representation, which which includes how the system works. It includes the causal relations. This is what enables you to predict. Uh, and And it turns out that we do have such a model of the world, and we it's not so much that we have specific expectations about what's going to happen next. What is happening most of the time is that things happen, and then we make sense of them.
Hmm.
That is, we actually go back and fit them into what happened before. And quite often, right now, you're not predicting what I'm going to say next, but I'm not going to surprise you by what I say. Or, if I said lumber all of a sudden, I would surprise you because it doesn't fit. But uh, so this is the way, the most interesting part of this works. And what is remarkable from the point of view of a psychologist, there are many, many things, but that touch on what Yann is doing. What's remarkable is how little it takes, how quickly people learn, and whether that I think is a fundamental puzzle. Uh, and and it turns out that the representation of the world that we have, uh, it's hard to imagine it completely without symbols.
Hmm.
That is, we do things symbolically, and how you represent symbols without using symbols is sort of a puzzle. So, I would ask Jan the question I've asked him before, which is whether solving a generic learning problem is enough to get all of that. That is, to get the system that we learn quickly and to get a system um, that will have the kind of logic that enables us, that there is a certain kind of mistakes that people just don't do. And so we have it that an object is not in this two places at once, or basic facts about the world, that and and there is sort of a certainty about it that seems to be difficult to achieve with just a, a system that learns approximately. So I was wondering,
Mhm.
how Yann is going to deal with that.
Yeah, yeah. Before we get into the answer, just a quick table setting. So the system one is the automatic, sort of the things that we do without thinking, and the system two is, or what we would feel like we're doing without thinking, even though we might be. And system two is more complex,
Yeah,
more
I was
complex.
so far. I was talking
Yeah.
everything I was saying. Was
Right.
system one basically,
Yes.
because
Okay.
I think the representation of the world that we have and our ability to anticipate or to feel
Hmm.
unsurprised by
Hmm.
what happens, which is I think more than anticipating. Uh, that
Hmm.
is all system one. That's all. That's all automatic. It's effortless and it's very quick. System two is we'll get to system two, but
Yeah.
solving system one seems to be a big one.
Yeah. Yeah. So yeah, we'll start on system one. Jan, your thoughts?
Well, I mean, I agree with Danny that current AI systems are very specialized, and that makes them very brittle because they're trained for one task or maybe a collection of tasks. There's a sort of a motion towards training relatively large systems for multiple tasks at once, not just one, because they tend to work better and require less data. But it is astonishing how fast humans and animals can learn new tasks when faced with sort of a new situation. How is it that um, a teenager can learn to drive a car in about 10 or 20 hours of practice, or learn to fly an airplane in 10 or 20 hours of practice? It's incredibly fast. If we were to use, let's say, reinforcement learning to train a self-driving car to drive itself, it would have to drive itself for millions of hours and cause untold thousands of accidents and destroy itself multiple times before it learns to drive, probably not nearly as reliably as a human. So what's the difference? Now, of course, obviously we can say humans rely on their background knowledge about the world, and that basically is the answer to that. We learn enormous amounts of background knowledge about how the world works. So we don't have to, when we learn to drive, we don't have to learn that if we drive next to a cliff and we turn the wheel to the right, the car will run off the cliff and nothing good will come out of it. We don't need to try because we know that from our model of how the world works, of intuitive physics and things like that. And this type of model is what gives us, in my opinion, some sort of common sense. I mean, what we call common sense comes out of this. That prevents us from making the really stupid mistakes that Danny was talking about that AI systems are doing currently. So how do we get machines to learn that? You look at how, at what stage in their life human babies learn basic concepts, like what is the difference between an animate and inanimate object, or I'm going to put this object on the table, is it going to stay stable or is it going to fall? That's learned around the age of 3 months or so, 3 4 months. Difference between animate and inanimate also comes pretty early. Object permanence comes very early as well. Some people claim it's innate, not clear. And then there are concepts that we take for granted. The fact that objects that are not supported fall; they're subject to gravity. Babies learn this around the age of 8 months, 8 to 9 months. It takes a long time to understand that an object that is not supported will fall. It takes a long time to understand momentum and things like that. Um, but then, by the age of 9 months, and so in the first few months, babies have very little ability to act on the world, right? They pretty much everything they learn is through observation only. Um, and by the time they are 8 or 9 months, they've pretty much understood the physics of the world. And babies are relatively slow. You take a baby cat, they understand intuitive physics incredibly quickly, and the dynamics of their own body and everything. So of course, it's not clear how much of this is hardwired, but there is clearly a lot of learning taking place. This type of learning is the one that we don't yet know how to reproduce with machines, and I think, that's where I focus my research. What is this type of learning that allows us to learn representations of the world and predictive models of the world that then allows us to learn new tasks very quickly with very few trials or very few examples. And it's a very hot topic in machine learning at the moment, actually.
Well, I'm curious about one thing. I mean, there are that I know about, and I'm quite ignorant about it, but there are two tentative answers that I know about to solve the problem of the speed of learning, and one is that a lot of is built in. So, uh, and 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 that looks very appealing because actually some animals really come out of the womb and they're ready to go. I mean, goats, mountain goats, they know how not to fall as soon as they are born. So uh, there it's difficult to think of learning. So nativism is part of the answer. Then there is something that I've been learning about, the hierarchical Bayesian models, which is sort of a different, that there are logical structures that we are prepared for to organize the world that we see, and that this is part of what enables us to learn things very quickly. Now, I think you reject both of these.
Well, yes. The first one only partially, because it's obvious that at least in certain species, including in humans, a lot of things are not necessarily completely hardwired, but at least we have sort of intrinsic motivation to learn them quickly, and it drives us to learn them quickly, essentially. And it's certainly true for baby ibexes and mountain goats and whatever, and certainly for simpler animals, like spiders and things like that. But it's even for an ibex or a mountain goat, they still need to kind of learn a lot about the dynamics of their own body. They're not hardwired with that. They're hardwired maybe with the geometry, but not with the details of it. And you can think of this as just being a few parameters to adjust, but I think it's much more what goes on in the brain of the animal is much more complex than that. So I think there is a lot of learning in there, even if in the end we can observe that the learning takes place really quickly. So then there is some evidence for the things that a lot of people in cognitive science think or have thought in the past, perhaps, that were hardwired for those things to be learned, because they can be learned really quickly. So, for example, it's relatively simple. It would be relatively simple for genetics to encode the fact that the visual cortex needs to be built with neurons that can detect oriented edges, for example. The kind of stuff that we find in the primary visual cortex area. But in fact, we have now a dozen different learning algorithms that, if we were to run them in real time in sort of a simulated animal, if you want, would learn those oriented feature detectors from almost random images within minutes. And so there is no point in hardwiring this because it can be learned within minutes. Same for face detection. So, you look at the brain, and there are areas in the brain that light up when people are shown faces. And so an easy conclusion of that is, oh, this area of the brain is specialized in face detection and is hardwired, and, face detection is innate, or face recognition is innate. But again, face detection can be learned in minutes. If you're a baby, your vergence is bad. Your focus is basically fixed at a relatively short range. So the only thing you see during the first weeks of your life are faces and nipples, essentially. And then you have a hardwired thing to pay attention to motion. And so within minutes, you're going to have a face detector in your visual cortex. Any reasonable learning algorithm will learn this extremely quickly. So you don't need this to be innate if it can be learned. So that's the first thing about the innate. Is it the case that the fact that the world is three-dimensional is innate, for example? It would make sense, right? Because our world is three-dimensional. All of evolution has always taken place in the three-dimensional world, so it would make sense to kind of hardwire this in the cortex. But then, if you're an AI scientist or engineer, you're like, how would I even define an architecture that has that hardwired? I don't even know how to do it. And so it's not clear you can actually encode this in the genome. On the other hand, you can learn it really quickly, because the fact that every point in the world has a depth is the best explanation for how your view of the world changes when you move your head, or if you correlate the two views from your left eye and right eye. And so learning things like very basic things like this is very simple for whatever learning algorithm or brain uses. So that's the first part about the sort of nature nurture debate, if you want. And then there is the second question of symbols, about symbols. So is it necessary to have explicitly hardwired mechanisms in our brain that allows us to do things like symbolic manipulation or reasoning? And I find that hard to believe, that they need to be hardwired. First of all, the first question to you, Danny, perhaps, which I've asked to many people who've come up with that question, is do you view the type of reasoning that, let's say, great apes do as symbolic, or do you view what monkeys do as symbolic, or dogs, or cats, or octopus? Do they do symbolic reasoning?
And can we also just, for table setting, define what symbolic reasoning is?
I don't know how to define it. I'm not a big advocate of
Okay.
the very existence of symbolic reasoning. So
Okay. We'll toss it over to Danny. Yeah.
I think that when we're talking about symbols, we're really talking about logical relations uh, that would I. That's not an easy one to explain. We understand each other, but it's
Yeah.
hard for me to explain. It, but I think a characteristic of symbolic reasoning is a certain discreteness, and it's not completely compatible with what we have talked about. I mean, this is interesting what is happening here because uh, I would um, I would push you with your idea that everything has to be learned or can be learned very easily. I would push you down the animal chain, where I think it becomes highly implausible. And you are doing the same thing to me with symbols by asking me, how far down do symbols go, and uh, and it's clear that the answer that the sort of the standard answer that it's connected with language and that the symbolic system and the language system are related and therefore other animals don't have symbols in the way that we do. Um, whether whether that is really compelling, I'm not sure. That is, in the sense, for example, that uh, in the hierarchical Bayesian models that I'd like to get your evaluation of. But those are supposed to take care of perceptual learning, and with the symbolic element or the logical element is sort of upstream of that in what categories of things there are, what categories of structure there are that you're about to learn. So.
right. So I think the there's a number of very interesting questions there. Well, so the first one is, what do we mean by symbols, really? And if by symbol we mean the ability to form sort of discrete categories, represent sort of discrete categories in our mental uh, representation system, then I think pretty much every brain has some sort of symbolic representation. And the reason I think this is that discretizing concepts, like having identified categories, makes memory more efficient, right? Because it makes representation uh, uh, have the ability to be error corrected, right? So if I write a zip code or a credit card number, and you make a mistake on one digit, that mistake would be detected because when you make a single error on a credit card number, there is some self consistency, right? And that's because credit card numbers not only are discrete, because they are numbers, but they are actually some distance apart. Like two credit card numbers are some distance apart from each other. So if you make a small error, you can snap it back to the correct one. You can detect the mistake, and you can, that's the basics of error correction. So just for the purpose of being able to do error correction, and for the purpose of being able to store concepts in memory, discrete concepts in memory efficiently, you need discrete representations. But now the big conundrum is, so in a way, you need symbols. And I think if that's the definition of symbols, then I think dogs have symbols. I don't know if they can reason logically. I guess they have some logic, certainly. I think cats and dogs and probably mice even have this kind of symbols.
And what's a discrete representation?
Okay, so I can give you. It's the difference between a real number and a natural number, right?
Mm-hmm.
So if I
go ahead.
Right.
Yeah.
So
okay.
let's say I send I want to send a number to you,
Mm-hmm.
and the only thing I have is a electric wire, and I can send a voltage, right? So I can send a voltage, 3 volts, let's say. But then at your end, it may not be exactly 3 volts because there is resistance, impedance, parasites, noise, whatever. So what you're going to observe is some sort of fluctuating thing that may be around 3 volts, but maybe a little shifted. But it's not going to be shifted all the way to 4 volts or 2 volts. It's going to be around 3 volts. So because you know that the signals I want to transmit to you are either 0, 1, 2, or 3, or 4, it's going to be 3, right? So despite the fact that there is noise in the transmission, and despite the fact that the signal is continuous, you snap it back to its correct value, okay?
Yeah.
So, and then to store that value somewhere, because there is only, 5 different possible values, 0, 1, 2, 3, 5, 1, 2, 3, 4, 5, you can store it with a small number of bits. Whereas if you had to store a precise voltage value, it would require many bits, right? So discretization makes memory more efficient, and it makes transmission either inside the brain or between agents reliable. It also gives the possibility of associative memory. So if you have in the brain, if you the brain represents things with voltages, right? To first order approximation. Now, there may be noise again in this representation, and you may see a partial view of an image, and you can reconstruct the whole image because of your knowledge of what the system is supposed to look like. You may never have seen my left side, the left side of my face, but even if you'd never seen it, you probably would have a pretty good idea of what it looks like because of your general model of a human face and the fact that they are mostly symmetrical. So that's an example of kind of snapping what's a noisy signal to a perfect signal because of the maybe discrete, maybe not discrete, but at least the structure, the internal structure of what you're looking at, which your brain has captured. So discrete, that's what discrete, why discrete symbols are interesting. It's the same reason, by the way, why all of modern communication is digital. It used to be analog. It used to be that to communicate with each other, we would call each other on the phone, and it would just transmit a voltage directly, from my phone to your phone. But now we replace this with digital communication with bits. And the reason is it's more efficient and more robust to noise, and there's all kinds of advantages. Our brains actually use digital communication internally. A neuron, neurons send spike to communicate with each other, and the reason is it's easier to regenerate a binary signal than it is to regenerate an analog signal, and it's more efficient energetically. There's all kinds of good reasons for this. So that may explain why symbols may emerge in all representations of the world, just for reasons of efficiency, and including for animals that do not have language. Now, of course, if you do want language, language is basically a sort of approximate way of representing the sort of complex data structures that we have in our mind, and to serialize it so that we can put that on a single one-dimensional signal, which is sound pressure, or sequences of words, which are symbols. And again, if I'm talking to you through a microphone, it goes through the internet, and there's some noise attached to that process. It's pretty high quality, but there's still some noise because our language uses discrete words. We can have error correcting communication. So even if you don't completely understand all of the syllables or phones that I'm pronouncing, you can still kind of recover what I meant. Because there is only a finite number of words, right? And you may not have heard all the syllables I pronounced, but you can snap it back to whatever makes sense in the context. In fact, every speech recognition system works this way. They have sort of a language model, and even if they don't understand every sound, they can sort of reconstruct really what was meant. In my case, it's even harder because of my accent. So language has to be discrete because it needs to be noise resistant, essentially. And perhaps language was the appearance of language, of symbolic language, was facilitated by the fact that we need to form the equivalent of symbols or discrete categories in our brain for efficient storage, and sort of recovery, associative memory recovery, possibly. And so it's quite possible that in the right condition, animals would have kind of more linguistic capabilities than we give them. And there's a number of experiments, of course, on this that have been done with monkeys and parrots and whatever.
Well, so in some sense, it's the discretization itself is built in. That has to be right. I mean that. But what you're saying is there is no content or very little content that is built in
to the human brain at inception.
Yeah.
Is that the okay?
Well, I mean, the big question is, where do the meaning of those discrete entities come from, right? Those and I certainly do not believe that the meaning of those discrete entities are predetermined in the human mind, certainly, and the animal mind either. Those are completely learned. And so here now comes the conundrum. So you're talking about hierarchical Bayesian systems. In a sense, multi-layer, deep neural nets are hierarchical Bayesian systems if you kind of view them the right way, and there are certain forms of them that are actually explicitly Bayesian. The main question in sort of the classical approaches to sort of Bayesian modeling is that the concepts in a hierarchical kind of Bayesian graph, a Bayesian network or a graphical model, people give them different names. Those concepts have to be designed by the human designer when they build those systems.
Yeah.
And it clearly is not happening that way in the brain. Those concepts are learned, right? So the basic entities that are manipulated are those kind of discrete concepts are learned.
Yann, can you sorry to ask, but can you just for the general audience describe hierarchical Bayesian systems?
Well,
Briefly.
okay.
Yeah.
I mean, it means different things to different people, but there is sort of a classical view of it called Bayesian networks, where you have basically it's a graph. So a graph in the mathematical term is a collection of nodes that are linked by edges, and the structure of this graph. So each node represents a variable. For example, so here's a classical example that people cite in courses on AI. There's a node that represents whether your house is jumping, okay, or is moving. All right. There's another node that indicates whether a truck has hit your house. Okay, and then there is another
Mhm.
node that indicates whether you're in California and whether there was an earthquake. Okay, so you could establish a causal relationship, or at least a dependency between those nodes. You can say, well, if my house just jolted, it's either because a truck hit it or because there was an earthquake, and there's probably not many other reasons for that to happen.
Mhm.
Now, if I look out the window and I see that a truck just hit the house, it immediately lowers my estimate of the likelihood that there was a simultaneous earthquake, right? Because the
Right.
likelihood of those two happening at the same time is very low. So that's called the explaining away thing. So you could imagine sort of building a network of those nodes where each node has a particular meaning. For example, some nodes would be symptoms that you can observe in a person, and then underlying nodes that are causally influence it would be sort of infection by a particular bug or whatever, right? And you could imagine building those things and then doing inference. So the value of some nodes, and you can infer the probability that all the other nodes that you don't observe have a particular value. I'm observing this and this and this and this symptom, and I have this graph,
Mhm.
and now I've measured the blood pressure and whether the person's tummy hurts or in particular way or whatever, and I conclude that it's probably appendicitis or whatever. So you can imagine, and in fact, systems in the 1970s were built exactly on that model for so-called expert systems or probabilistic expert systems. And what
Mhm.
we now call Bayesian networks and hierarchical Bayesian models and whatever are kind of the descendant of this, if you want.
Right.
Now, this does not involve any learning. All those things would be built entirely by hand, okay,
Mhm.
completely engineered. And that was essentially that necessity was one of the reasons of the kind of decrease in interest in sort of good old-fashioned AI
Yeah, these were
that
your
people were practicing in
competitors.
the 1980s,
The
because
Bayesian, yeah, the Bayesian folks were like,
not
don't listen
necessarily
to Yann.
Bayesian. It could be completely
Right,
logical
right.
and
Okay, got it.
hard decisions. But the fact that you had to hand engineer those entire systems from scratch
Mhm.
is kind of a little bit what killed them. So the alternative is learning. But now you have the question, how do you learn those concepts? How do you learn that you want to do computer vision? The nodes at the bottom level are pixel values.
Mhm.
Okay, what would be the right node just above that represent good combinations of pixel values? How do you learn that? Turns out those combinations would be things that detect oriented edges, which is what you observe in the brain and what convolutional neural nets actually learn. But that has to be learned. So then the big conundrum is, if a system is to learn and manipulate discrete symbols, and learning essentially requires things to be kind of continuous, how do you kind of make those two things compatible with each other?
And the
That's
answer?
I don't know. Maybe the answer is that we are giving perhaps a little too much importance to logical reasoning. So it's one thing that Jeff Hinton is saying, which is which I agree with to a large extent, which is a lot of reasoning in certainly in animals and in humans is not logical reasoning. It's basically simulation or analogical reasoning, which kind of similar. So you're a lion in the savannah and you're kind of chasing a wildebeest or something, and you have to do some prediction about the trajectory of the wildebeest, and work with the other lion or lionesses usually to kind of chase the animal in the right way, and that requires uh, kind of a simulation of the animal you're chasing. The best way to predict how the animal you're chasing is going to act is to have an internal model of that you can simulate. And it's the same, like so in a more kind of human situation of you want to build a widget, like a box out of planks or whatever. You have to have sort of a model in your mind of what will be the result of assembling those planks, and how solid it is going to be if you use glue or nails or screws or kind of more complex carpentry. Uh, and so the key element in this form of intelligence is your ability to build models of the world, predictive models of the world. And that's what we're missing. Okay, that's what we need to figure out how to do with machines.
And you can do this, and I find this very convincing, actually. I mean, so you can do this without symbols. You can do this without an explicit representation of causality. Uh, you just observe, and from the observation, you can go directly to prediction.
Right. So there is going to be some causality involved. The question is whether you again need an explicit mechanism for causal inference. But if your model of the world includes the prediction of the next state of the world, given the previous state and given your action, then you're going to build a causal model, right? Because you know that your action or the action you observe from other people or other agent uh, will tell you, if I take that action, I will get this result from this state, right? So you will be able to establish causal models if you can act or if you can determine that another agent has acted and you've observed the result.
I mean, mechanisms of that kind certainly exist, in human physiology. So, uh, any movement of the eye involves a prediction of what the world will look like when your eye moves. And there are those beautiful
Absolutely.
old experiments where uh, people, in fact, you use curare to paralyze their eyes, so they can't move their eyes. But when they intend to move their eyes, the world moves, and
That's right.
and so they're anticipating. So, and that is clearly, nobody would claim that there is any symbol or any causality required to do that. This is the kind of thing. So that would be your model
Right.
for.
In fact, your perception of the world is not the world as it is; it's the world as it's going to be, because there is, about 100 millisecond delay between what you see and how your brain interprets what it is. So in fact, your brain predicts 100 milliseconds in the future. Your estimate of the world that you are consciously aware of
Absolutely.
was predicted from your perception from a tenth of a second ago. And that takes place everywhere. So, one of the current main theoretical concepts in systems neuroscience or computational neuroscience is this idea of predictive coding, where basically everything in the brain is trying to predict everything else in the brain, and predict future action, future state of other parts of the brain, and things like that. Now, this doesn't mean that people who are pushing for this kind of theory know how the brain works, because between a general concept of this type and sort of reduction to a practical algorithm, if you want, that you could sort of implement on the machine, there's a huge distance that has not been uh, been bridged yet. So that's kind of a big program, I think, for science for the next few years.
I was curious earlier, and it's a question I neglected to ask, but that was about face detection and the existence of a face system. It seems to me that seeing your mother's face a lot uh, doesn't really equip you to distinguish between faces,
That's right.
and that's what the face system does. I mean, it's not only recognize this as a face; it is actually specialized in identifying faces. That is, and uh, that ability to learn very quickly a distinctive face, that seems to be, I mean, it's the same problem. Again, I don't quite see how that gets done.
I don't know. Historically, also in computer vision, face detection preceded reliable face recognition by a decade or two. So we had reliable face detectors in the early 2000s, and reliable face recognition didn't pop up until 15 years later, roughly, with deep learning methods, actually. Um, and it works surprisingly well. So you don't need a big neural net to be able to recognize,
To
more people,
identify faces.
identify faces, and have a system that recognizes more faces than any human can, with the same level of accuracy. Maybe not with the same sort of robustness to different changes in pose and facial hair and things like that, but But in terms of number of different people being able to put a name on, they're incredibly good, incredibly reliable. So it may not be that hard of a task as we thought, perhaps.
I kind of thought that this was going to be a discussion more of how we could transpose learn from the human brain and turn that into AI. But it seems like we're actually talking a little bit about how we can learn about the human brain from the construction of AI.
I think that this is actually happening. But there is an interesting question to me as a psychologist. It's a version of the Turing test. So, what would it take for the computer to fool you that it's human? And and I was thinking that one characteristic of it is mistakes that strike us as absurd. That is, uh, and they seem to violate some basic constraints. I mentioned earlier an object not being in two places, and there is, I think, a finite set of absurd mistakes. Or am I wrong? And, and would it be part of? I mean, would it be of any interest to have a system that makes the same mistakes that avoids mistakes that people consider absurd, and that makes mistakes of the kind that people tolerate? I mean, is there such a category of absurd mistakes in your field?
Well, it, well, there's different kinds of mistakes, right? I mean, there are computer vision systems that make stupid mistakes because so in the past, when computer vision systems, were like maybe 15 years ago, computer vision systems were okay at picking out recognizing objects in images, but they were sometimes confused by the context. And people, they were not confused by the context, they just were not using the context at all. And so, a system would make a mistake of recognizing a face that wasn't really a face, and from the context, you could tell it wasn't a face, or would recognize an object that had the shape of I don't know, a cow or something. You can tell from the context that it cannot possibly be a cow if you're a human. So that was the big criticism towards computer vision system. They don't take context into account. And now the criticism you see is that they take too much context into account. So there is this famous example of a modern vision system. I mean, it's a system of a few years ago. You train it to recognize things like cows and trains and airplanes and cars and stuff like that by showing it thousands of examples of each category. And then you show it a cow on the beach, and it can't recognize it as a cow because every example of cows it's seen were on green pasture. And so the system actually learns to use the context, and it uses it too much. And the context was, had a spurious correlation with the category. And the system doesn't have the common sense to say, well, that's a cow regardless of, because a cow could be very well sitting on the beach. So then how do you fix that? And
I mean, how do you get that common sense? I mean, that seems to
get the
be.
common sense. Exactly. So I think this is not going to be solved, in my opinion, by more tweaks on the architectures and more training data and things like this. I mean, it may be mitigated, but I think it's not going to be fixed by that. I think it's going to be fixed by systems that basically learn models of the world and then have the ability to tell that it's perfectly possible that a cow could be on the beach. That's that's the kind of compositional nature of the world that even combination of things you've never seen can very well happen.
And that is already happening.
Not
There are
really.
systems.
So there's a thing that very interesting thing that is happening, which is one of the hottest topics, as I was mentioning earlier, in AI today is, or in machine learning at least, is this idea of self-supervised learning, which I've been a big advocate of for many years. And it's the idea that you train a system not to solve a particular task, but to basically learn to represent the world in sort of a semi-generic way. And you train it by basically you train it to predict, essentially. Okay, so this works wonderfully for natural language understanding system. The standard way nowadays that has become standard over the last 3 years of training a natural language understanding system is you take a sequence of words, a sentence or something longer than that, maybe a few hundred words or 1,000 words, and you mask about 10 or 15% of those words. You replace them by a blank marker, and you train some giant neural net to predict the words that are missing. Okay, and in the process of doing so, the network learns the nature of language, if you want. So it learns that if you say the lion chases the blank in the savannah, the blank is likely to be something like a wildebeest or an antelope or whatever, right? But if you say the cat chases the blank in the kitchen, that's probably a mouse. So a lot of semantics about the world, certainly the syntax, but also the semantics about the world, ends up being represented by this network that is just trying to predict missing words, right? Now, of course, the system can never predict exactly which word is missing. It could be antelope or wildebeest or zebra or whatever. But it can easily represent a distribution over words, like a probability distribution over words, because there's only a finite number of words in the dictionary in English. So you just have a number, which is a score for how likely it is for this particular word to appear, and that's how the systems handle the uncertainty in the prediction.
Yeah, I mean,
Well,
and the results are sort of amazing. You get text that sounds like text in a particular style, and it's coherent and it's grammatical, uh,
but it
and
makes stupid mistakes. It makes very stupid
it
mistakes,
makes absurd mistakes.
absurd mistakes. Yeah,
Yeah,
because
and I
yeah.
was wondering, well, when does it say that it makes absurd mistakes? It's a question that we talked about before, whether it do- whether it knows what it's talking about, and the sense is that if you just merely predict words, there is no content there. That purely predictive system uh,
Well,
doesn't know
I don't
anything.
know. There is
But
a little bit of content, but it's very superficial, right? So the understanding of the world by those systems is superficial. There is some understanding, but it's very superficial. So yeah, if you ask questions like, um, uh, is the fifth leg of a dog longer than the other four? The thing will say yes or no, right? I mean, it won't tell you dogs have four legs, right? Um, and things of that type. They can't count. I mean, there's a lot of things that they can do, and it's because they don't have any common sense, and it's because all of this learning is not grounded in an underlying reality. It's basically just from text, and the amount of knowledge about the world that is encoded in all the text in the world that those systems have been trained on, and it's billions of words, is not present. Like most of human knowledge is not represented in any text in existence. For example, I take an object, I take my phone, and I put it on the table next to me, and I push the table. Because of your physical intuition, that the object will move with the table. When I push the table, the object that is on top of it will move with it. Right? There is nothing in any text in any part of the world that explains this. And so a machine that is purely trained to predict missing words will not learn about this, which are sort of really basic facts about the world. So I'm one of those people who believe that truly intelligent systems will need to acquire knowledge, will need to be grounded in some reality. It could be a simulated reality, it could be a virtual world, but it has to
Metaverse.
be an environment that has its own logic and its own constraints and its own physics. And
so you think that in principle, if you took those transformer and you put them together with, if you put them to work on videos,
right.
if you if you put language and videos together, is that going to be a qualitative advance, and is that beginning to happen?
Well, yeah. So yes and no. So I think you should start with just video. Like, can you build a neural net that will, or some learning system that will watch video all day, and basically learn basic concepts about the world just by watching video. The world is three-dimensional. There are objects in front of others. There are objects that are animate. There are objects, whose trajectory is completely predictable, inanimate objects. There are objects whose trajectory is not completely predictable, like the leaves on a tree, but qualitatively you can. So there's some level of representation where you can predict what those things do. And then objects that are very difficult to predict, they are animate objects, humans and things like that, right? Or chaotic systems and whatever. And so, a lot of research goes into this, essentially. None of them work at the moment. There's a lot of systems that attempt to do video prediction and basically attempt to learn representations of the world that are, in an abstract way, can learn to predict what's going to happen in the video in the long term. They all work within a few frames of a video, like a fraction of a second, but then the predictions go really bad, and the representations that are learned by those systems are not very good. We can test them by using the representation as input to, let's say, an object classification system, for example, and measure, how many samples does it take for the system to learn the concept of elephant, right? Does it still need 3,000 samples, training example, or would it work okay with 3 or 4?
And the
And those things, the answer is training from video, they don't work very well. There is one thing that is starting to work, and that gives us a lot of hope. So a particular form of self-supervised learning, where you can assimilate the video if you want. So you take an image, and you transform this image in some way. You change the colors a little bit. You change the scale, the orientation. You translate it a little bit. You do some manipulation to it. It's called data augmentation. And then you train a neural net, or 2 neural nets rather, to basically map those 2 images to the same representation, the same vector. Typically, it's a vector, right? A list of numbers, typically a couple thousand. And so that's easy enough. You have 2 images that basically represent the same content, 2 views of the same object, for example. And you train the system to tell you, well, learn a representation that tells you the content of the image and not the details. The difficulty is, how do you make sure that when you show 2 different objects, it will produce different representations? And avoiding this problem. This problem is called the collapse problem, and the big question is how you avoid this. So there's a lot of work now, really interesting work on what's called contrastive methods and also non-contrastive methods to do this. And I'm really excited about this area of research because I think it's the germ. I think it's our best shot as to a path towards learning, getting machines to learn abstract representations, and predictive models, where those predictive models will not take place in the space of pixels, but will take place in the space of, or whatever it is that your input is, but in the space of abstract representations.
And you think that the architectures that exist now will eventually, that is, it's not going to take a different architecture?
Well, I think the architecture is not the crucial question here. I think the architectural components are already here. What I think is not here is the whole learning paradigm. So let me take an example, right? We can build a giant neural net where you feed it a few frames of a video and you train it to predict the next frame or the next few frames. You can do this with least square, right? So just measure the sum of the square of the differences between the values of the predicted pixels and the pixels that actually occur in the video. And when you do this, the predictions you get from your neural net are blurry. You get very blurry images as the prediction. And the more you let the system predict far in the future, the more blurry the predictions are. And the reason for this is that you ask the system to make one prediction, and the system cannot predict a priori if it's a video of us talking. It cannot predict if I'm going to move my hands this way or I'm going to move my head to the left or to the right. And so the only thing it can do is predict some sort of average of all the possible things that can happen. And that would be a very blurry version of us. So that's not a good model of the world. Now, how do you represent the uncertainty in the prediction? So in the case of text, it's easy because it's discrete. You can just have a distribution over which word are possible, but we don't have a good way of representing distributions over images, for example. So that's why those techniques don't work currently for video prediction. And whatever representations they learn actually are not very good.
That's
But yeah,
and that's because of the sheer complexity. I mean, is it a quantitative problem, or is it a point where quantity becomes quality?
no, it's not a question of we don't have enough data or computers are not powerful enough or neural nets are not big enough. It's a question of principle. It's a question of like what is the right objective function, what is the right way of representing uncertainty, and then technical questions like how do you prevent this collapse I was talking about, which I didn't explain very well, but which is a more technical issue. But it has to do with basically representing uncertainty in the prediction. The fact that there are, when you have an initial segment of a video, there are many ways that are plausible to continue it, and the machine has to basically represent all of those or a good chunk of those possibilities.
And it would have to be predictive. That is, it couldn't work backward.
It could work both ways. It doesn't
But
even have to be
backward is
temporal.
the way that I think the mind works.
Oh yeah,
It,
sure,
it really, you get prediction very short term, but by and large, a lot of
sure.
it is simply making sense after the fact.
Oh,
You don't
absolutely.
need to predict everything.
Yeah, I mean, if you're a police inspector, you get to a scene and you have to basically figure out how it got there, right?
Yeah.
Whether it's a sequence of event that led to this. So yeah, I mean, I think I use the example of prediction of future event, but it could very well be prediction of things you do not currently perceive, right? So you do not currently perceive the back of my head, but you have a pretty good idea what it looks like, and if I show it to you, then you can correct your
Not
internal model.
surprised.
You're not very surprised, but maybe if I had a ponytail, you would be surprised, slightly more surprised. Uh, so it's not just prediction in time. It can be prediction in space. Predicting a piece of an image from another piece, predicting a piece of a percept that is currently occluded or not can it be obtained, and retrodiction, predicting the past, which you have not observed from the present, and maybe an evolution. So yeah, I'm not insisting that it has to be forward prediction. Forward prediction is useful for planning. So if we're talking about a form of reasoning that would be planning a sequence of actions to arrive at a particular result, then what you need is a forward prediction that will predict the state of the world as when you take an action.
Well, I mean, the amount of progress that is occurring in your field is just amazing. It's
I have a hard time following,
I'm
actually.
very envious. I'm very
I don't know.
envious because now a few years ago, I think I heard you say about a research program that we have the cherry, but we don't have the cake. But that's you recognize that as
Oh, absolutely. Yeah, this has become a bit of a running joke in the community now. I use the analogy of the cake to say that to basically sort of make very concrete the fact that most of what we learn as humans and animals, and in the future that machine will learn, is learned in this kind of self-supervised manner, basically by watching the world go by and by taking an action once in a while, but in a non-task specific way, learning how the world works. Self-supervised learning, that's the bulk of the cake. So if intelligence is a cake, the bulk of the cake is this type of learning. That's where we learn everything. And then there is a thin layer of
reinforcement learning.
There is supervised learning, right? You're taught at school, or your parents, teach you something, or you read a book or whatever, or you show a young child a picture book and you say that's an elephant, and baby say elephant, and with 3 examples, the baby has figured out what an elephant is, toddler, what an elephant is. So that's supervised learning. And then there is reinforcement learning, where you learn a new skill by trial and error, and you get rewarded by your own success or not. And that was the cherry on the cake. The supervised learning was the icing, if you want. And this was sort of a metaphor to tell people, like, we're currently focusing on the icing and the cherry, but we haven't figured out how to bake the cake yet. And so I use this joke saying that this was the dark matter of intelligence, because it's kind of like physicists, right? They tell you dark matter exists, and it's most of the mass in the universe is dark matter, and they have no idea what it is. It's very embarrassing. So we're in the same situation. Again, a physicist, it's even worse, because there's dark matter and dark energy, and the combination of the two represents something like 95% of the mass in the universe. So that's really, really embarrassing, and we have no idea what it is. So we're in the same situation, which means we have a lot of work to do. Our
Yeah.
understanding is.
I mean, is the progress in your field exponential?
Yeah, but before you answer,
I
I'm
mean,
just watching the clock. You guys can go as long as you want, but I'm just
no.
saying that whenever you're
Oh, yeah.
ready.
Oh,
Yeah.
yeah. I'm past
You have
my
a hard.
hard stop. Just
You
Okay.
answer
have
this question.
Okay. Sounds good.
I think it's increasing because there is more and more people joining the party, and more governments and companies investing money in it. So you see a growth. You see a growth in applications. You don't necessarily an exponential growth in sort of new concepts, but there are new concepts that are coming up at a surprisingly high speed. And so I guess one big question is, one question is, are we going to have another AI winter like there were in the past? And my answer to this is probably no, or at least not to the same extent that we had in the past, because there's a big industry now behind AI. It's useful for a lot of things. You take deep learning out of Google and Meta and a few other companies, and they crumble. I mean, they're completely built around it now. So and certainly there's a lot of other areas also. Um, so I think it's not going to collapse as it used to. The question is, are we going to make this next step towards machine common sense, self-supervised learning, etc., before people funding all of this get tired? And that I don't know the answer. I'm just
I see.
hoping that we make progress fast enough.
Fascinating question. Thank you, Yann. I've
Well,
learned a lot.
thank you, Danny. It's always a pleasure chatting with you.
And thanks to both of you. It's
Thanks
amazing
for having us.
to hear you talk about this. I feel like I was just in like an ultra graduate level course. We should have more psychology and AI together, because this is, I think, like, it's just amazing to hear you guys bounce these concepts around. And in terms of energy, Jan, clearly there's energy in the field. It's amazing hearing you. No drop from the 5 years we've known each other, maybe even more. So thank you, Danny. Thank you, Jan. So great having you here.
It was,
Yeah,
it
let's
was
do
an
it again.
instructive pleasure.
Yes, I'd
See
love to
you.
do it
Good
again.
for me. Thank you, Alex.
Okay. All right.
See you
Thank
guys.
you.
Bye-bye.
Take care, Danny. Thank you to
Yeah.
Nate Gwatney for doing the editing, Red Circle for hosting, and all of you, the listeners. We'll be back next Wednesday for another episode of the Big Technology Podcast. Until then, we'll see you.